Section 6.2, we're going to start out of sync in this class. We're going to start with chapter 6 first, then 5. So 6.2, trigonometry of right triangles. So let's specify what everything is. A triangle, I'm just reading the definition right there. A triangle with one 90-degree angle, and the 90-degree angle is denoted by that right there, is called a right triangle. We have two types of angles. In this section, in this chapter, we're going to focus mainly on acute angle. That's an angle between 0 and 90 degrees. An obtuse angle, that's more for trig, that's later on, that's bigger than 90. So if we're talking about a right triangle, then for sure, the angles that you choose in a right triangle, the other two angles, if one angle is 90 degrees, that doesn't look pretty. Okay. If you take those two angles, call this alpha, call this beta. So alpha and beta must both be acute. Remember, the sum of the three angles in any triangle must add up to 180. If one angle is 90, the other two angles can't be more than 90 each. So they both must be less than 90. Together they should add up to 90. Now, given a right triangle, we know two things about it. One, we know it has one 90-degree angle. Secondly, we know that the side opposite of the 90 degrees is called the hypotenuse. And if I take the hypotenuse squared, that is the sum of the squares of each side, or geometry insists on legs of the triangle, whatever you like. Pythagorean Theorem. So we need to know that, and we need to know that given a right triangle, if you pick an angle theta, now the fixed angle is 90 degrees. The side opposite of that is always the hypotenuse. And wherever I choose the angle, so it depends where theta is. If I choose the theta to be right there, then the side opposite of it would be labeled the opposite of theta. The hypotenuse is always fixed. So the one side left that we didn't label, we call that the adjacent. So associated with every right triangle are three sides. The hypotenuse is fixed, but the angle theta would depend on where you the sides, the opposite and the adjacent would depend on your choice of theta. And with each triangle we have 6 associated trigonometric functions. The sine of that angle theta would be the ratio of the opposite side of the triangle divided by the hypotenuse. The cosine of theta would be the ratio of the adjacent divided by the hypotenuse, and the tangent of theta would be the ratio of the opposite divided by the adjacent. So this is something that you need to really get down and memorize. And a simple way of remembering that is SOHCAHTOA. That's what I was taught back in the days. Sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite of the adjacent. Make sure to memorize it correctly or spell it correctly. Now, associated with sine is cosecant. Cosecant of an angle is the reciprocal of the sine. Secant of an angle is the reciprocal of cosine. And cotangent of an angle is the reciprocal of tangent. And those, hopefully, we're going to get down and use in this section and in every section. Now, the catch comes up. This is all for the angle theta. if I was to call this angle beta, you'll notice the hypotenuse would still be fixed. That wouldn't change. But this side would be the opposite, and this side would become the adjacent. And now, based on the new information, you would go for beta, but the sides are no longer the same. So that's one thing you gotta be careful with as you really work this out. We're gonna look at some examples and apply this. And here we go. In the first problem, first example, we're given the three sides. So, not much to do except pretty much figure out where the angle is. The angle theta is right there. So the side opposite of the 90 degrees is the hypotenuse. The hypotenuse is 13. And the side opposite of the angle is 12. And the remaining side is the adjacent. When it says find the 6, I normally list the first 3 and assume you could find the other 3. But in the first few examples, I'm going to find all 6. So if I want to find the sine of theta, I know that's the opposite over hypotenuse. The opposite of this angle is a 12, and the hypotenuse is 13. If I want to find the cosine of the angle theta, that's the adjacent over the hypotenuse. The adjacent is a 5, and the hypotenuse is 13. And if I want to find the tangent of theta, that would be the ratio of the opposite side of that angle to the adjacent. The opposite is a 12, and the adjacent is a 5. And once I figure this out, cosecant of theta would be the reciprocal of those. Secant of theta would be the reciprocal of that. And cotangent of theta would be the reciprocal of tangent. And that's pretty much it. If I look at example of part B, I noticed they didn't give us 3 sides. They only gave us 2 sides. Well, we know about Pythagorean, right? Pythagorean theorem, we say, all right, no problem. We know that the hypotenuse squared, that's the hypotenuse, is 3 squared plus 2 squared. The hypotenuse squared is 9 plus 4, which is 13. And when you square root both sides, the hypotenuse would be plus or minus the square root of 13. Length cannot be negative, so it's going to be a square root of 13, at least in geometry. And once I get that side, now the second part I have to be cautious with. There is my angle theta. The side opposite of 90 is always the hypotenuse. I don't have to worry about that. But the side opposite of the angle is my opposite. That leaves me with an adjacent of 3. And now if I find the sine of theta, that's the opposite over the hypotenuse. That's 2 over radical 13. And if you rationalize, multiply by radical 13 over radical 13, that would be 2 radical 13 over 13. And if I take the cosine of theta, that will be the adjacent over the hypotenuse. The adjacent is a 3 over radical 13. And if you rationalize, 3 radical 13 over 13. And the tangent of that angle, oh, I'm sorry, I'm still stuck on theta. I mean beta. That would be the opposite over the adjacent. The opposite is a 2 and the adjacent is a 3. And I'm assuming you could find the remaining 3. Cosecant would be the reciprocal of this. Secant would be the reciprocal of this. And cotangent would be the reciprocal of this. And if I look at part C, I notice also they didn't give me all the sides. Well, I could figure out what the sides are. That is, I could say, you know, I could lift that up a bit. It gives me more space. Yeah, like that. There we go. So I could say here, you know what? Hypotenuse, call this side M, So I could say 5 squared equals m squared plus 2 squared. 25 equal m squared plus 4. M squared equals 21. And when I square with both sides, m would be plus or minus square root of 21. In geometry, length cannot be negative. And there it is. And as far as this angle is concerned, the hypotenuse is 5. The opposite is a 2. And the adjacent is a square root of 21. And the sine of alpha, that's alpha, is the opposite over the hypotenuse, that's 2 over 5. The cosine of alpha is the adjacent over the hypotenuse, that's square root of 21 over 5. And the tangent of alpha is the opposite over the adjacent, and that is 2 over radical 21, which is radical 21 times 2 over 21. And the cosecant of alpha is the reciprocal. The secant of alpha would also be the reciprocal, 5 over square root of 21. And if you rationalize, that's 5 times the square root of 21 over 21. And the cotan of alpha would be the reciprocal of this, which is square root of 21 over 2. Now, if you recall from algebra, complementary angles and supplementary angles. Complementary angles would be when two angles add up to 90 degrees. And do we agree that if this is 90 degrees, then the sum of those two must be 90? Directions here says, find the exact value of the following trigonometric functions. What is the sine of alpha? Well, you notice that there are letters. There are no numbers. Well, as far as alpha is concerned, if I take alpha into account, that's the opposite. The hypotenuse is fixed, and that's the adjacent. So, sine of alpha would be the opposite over the hypotenuse. That's the letter N over the letter K. And what would be the cosine of beta? Well, beta is right there. Hypotenuse is fixed, but as far as beta is concerned, that is the opposite. And that is the adjacent. So, cosine of beta is the adjacent over the hypotenuse. The adjacent to beta is N, and the hypotenuse is K. Alright, before I make my conclusion, let me do the next problem. Oh, that should have been secant, my mistake. Sorry. If I take the secant of alpha, alpha is right there. Secant of alpha is the hypotenuse over the adjacent. The hypotenuse is a K. And the adjacent of beta is an M. And since I'm at it, if I take tangent of alpha, that's the opposite of alpha over adjacent. So maybe I should have did that from the beginning, so I wouldn't confuse you. Let me just stick with the bluish part. I mean the yellowish, right? And if I look at that, well, tan of alpha is the opposite, which is n over the adjacent, which is n. Done. Now, if I would go ahead and look at this from beta's point of view, as far as beta is concerned, the hypotenuse is fixed. This side, as far as beta is concerned, is the opposite. And as far as beta is concerned, this is the adjacent. So when I say the cosine of beta, that's the adjacent over the hypotenuse. When I say what's the cosecant of beta, that is the hypotenuse over the opposite. As far as the blue is concerned, the hypotenuse is k, and the adjacent of beta, the opposite of beta is actually m. And if I look at part C, taking the cotangent of beta, and again I'm looking at the blue, that is the adjacent over the opposite. The adjacent would be the n, and the opposite would be the m. And what do I conclude? Well, if I look at the complementary, doesn't that mean that alpha equal 90 minus beta, or beta equal 90 minus alpha? That means if I know one angle to be 10 degrees, I would know automatically that alpha is 80 degrees. That's what it means to be complementary. If alpha is 30 degrees, then I know beta must be 60 degrees. And here I've just shown that the cosine of one of these angles is the sine. It equals the sine of 90 minus that angle. And I'm using this right here. And vice versa. I could say the sine of alpha is the cosine of 90 minus alpha. So any given angle, as long as we are dealing with a right triangle, this is true. And similarly, I know that the secant of alpha is, again, those are equal, is the cosecant of 90 degrees minus alpha, meaning the secant of 40 degrees is the secant or cosecant of 50 degrees. They must add up to 90 degrees. And similarly, the cosecant of beta or alpha is the secant of 90 minus that angle. And the same deal here, the tangent of alpha is the cotangent of 90 degrees minus alpha, and the cotangent of alpha I could say is also the tangent of 90 minus alpha. I could use beta, it really doesn't matter. So that's my conclusion. If I have the sine of 40 degrees, I could say that's the cosine of 50 degrees. Very simple. As long as the two angles add up to 90 degrees, I'm okay. Now, I want to look at two special triangles. And here they are. If I look at a triangle 45, 45, 90 and 30, 60, 90. If I look at 45, 45, 90, if this angle is 45 degrees, automatically this angle is 45 degrees because they must add up to 180. That makes this an isosceles triangle. That is, if I call this side A, this side is automatically A. And I know that the hypotenuse squared would be the first side squared plus the second side squared. And the hypotenuse squared would be 2a squared. And if I square both sides, I'll get a plus or minus. Ignoring the negative, that will be radical 2a. Now, what does that mean? That means, since I used A, given any 45, 45, 90 triangle, if I figure out what the side opposite of 45 degrees is, automatically the other side will match, and the hypotenuse will be that side multiplied by radical 2, no exceptions. And that's what we're going to play with for a while. Now the important aspect of this is that the trig functions don't change. The sine of 45 degrees is the opposite. Which opposite? It doesn't matter, they're both the same. The opposite over the hypotenuse. The cosine of 45 degrees is the adjacent over the hypotenuse. And the tangent of 45 degrees is the opposite over the adjacent. And there it is. Those are fixed. How can you derive them? By copying this, because that's going to always work. And can I always do that? Absolutely. Anytime I need this, I would go ahead and draw a triangle and say, well, look, if you make that 90 degrees, if this is 45 degrees, this is automatically 45 degrees. Whatever this side is, this side automatically is, and this is radical 2 times that side. What does that mean? That means if I gave you the following triangle, now I'm going to use a bit of geometry. I know you're going to remember geometry, but that's okay. If I was to tell you that this side is 3, you would know automatically this side is 3. So the given is the black portion. If you were to tell me that this is given, I would know automatically this is a 3, and that makes this a radical 2 times that 3. If you tell me, given that this is a 10, well, I would know automatically this must be a 10, and this must be a 10 times radical 2. If you are to tell me that this is 5 radical 2, then I would know automatically that what do you multiply this side with to get 5 radical 2? Well, whatever this side is times radical 2, that must be a 5, and that must be a 5. So that's how I figure out the relation. That is, this relation is going to always hold. You could alter the sides anywhere you want, as long as you do the same thing to each side. So, when I made this 3, I must have multiplied this by 3 over a, multiply this by 3 over a, and multiply this by 3 over a. The a's cancel out, and there it is. You could do that anytime you want in a triangle. Any triangle, not just a right triangle. In any triangle, that's geometry. Right? And if I wanted to make this 5, I could. That's automatically a 5, and this is 5 radical 2. Now, if I wanted to make this a 1, wouldn't this automatically be a 1? And this would be a radical 2? That would be the star triangle that you're going to write down 1/3 of the time in this class. 1/3 of the time in this class, you are going to write that triangle because you're going to need it. Right? 1/3 actually is going to be this triangle and this triangle. Now, if I look at this second triangle, and the reason I would write this down, because I need to know the sine, cosine, and tangent. So, if I look at this triangle, this is 30. If I call this A, this is automatically 60, but unlike the previous problem, that doesn't get me anywhere. So what I do, I draw an auxiliary figure. That is, I copy that triangle, reflect it with respect to that line, making this as 30 degrees. And if this is 60, making this automatically as 60 degrees. What that does, that creates an equilateral triangle. 3 equal sides, 3 equal angles. If this is A, this is automatically A because this is an image of this. So this length is 2A. That makes this 2A, and that makes this 2A. And now if I eliminate this auxiliary figure, if I take it out, say, you know what, I don't want it anymore. What I get, I figure that, hey, if the side opposite of 30 degrees is A, the hypotenuse is 2 times that. And I could figure out the remaining side, call this side M. I could say 2A squared, the hypotenuse squared, is M squared plus A squared. So I could say 4A squared equal M squared plus A squared. M squared would be 3A squared, and M would be the square root of 3 times A. So, this is what I know. If this side opposite of 30 degrees is A, the hypotenuse is automatically 2 times that, and I just figured out the remaining side, which is the side opposite of 60, to be radical 3 times that side. So everything is tied with the side opposite of 30 degrees. And what's so important about that? I'm gonna run 2 triangles for you really quick. And again, from geometry, if I label this side 30, this side's automatically 60, this side 30, this side is automatically 60. If I told you this is 5, well, how do you get a 5? Don't you multiply this by 5 over A? Multiply this by 5 over A, you could multiply this by 5 over A. Or you could even go easier way would be, we know whatever this side is, the hypotenuse is always 2 times that. 2 times 5 is 10. And this side here is whatever that side is times radical 3. And if I told you this side right here is 7 halves, a really bizarre number. Well, you know the hypotenuse is 2 times that. And this side is radical 3 times that. Now, what's so important about this triangle? Well, if I really was to go ahead, and this is the one I'm gonna use most of the time, I know I'm shrinking, I'm gonna rewrite this over and over and over. If you're missing any of this, not to worry. If you call this 30 degrees, I could say if this is 1, the hypotenuse is 2 times 1, which is 2, and the side opposite of 60 is radical 3 times 1, which is radical 3. And this is the one triangle we're gonna use. So those two we're gonna use 1/3 of the time in this class. And what's so important about them? If I look at this and I say, hey, what's the sine of 30 degrees? What's the cosine of 30 degrees? And what's the tangent of 30 degrees? Or what is the sine of 60 degrees? What is the cosine of 60 degrees? And what is the tangent of 60 degrees equal? Sine of 30, there's 30. The opposite over the hypotenuse, 1/2. You could use this, of course. You could say A over 2A, which is 1/2. Cosine is the adjacent. The adjacent is radical 3 over 2, radical 3A over the hypotenuse, which is 2A. Those cancel out, and you're left with radical 3 over 2. This is more beneficial. Cosine is the adjacent over the hypotenuse. And tangent is the opposite, which is 1 over radical 3. And if you rationalize, that's radical 3 over 3. If you go to 60 degrees, this angle, sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent is the opposite over the adjacent. And I notice those are equal and those are equal because those are coterminal. Now this video I'm going to stop here and I'm going to pick this up in the next video.